Welcome everyone. My name is Tom Papatheodore with the OLCF. Today we're joined by Bob Corbella of NVIDIA, and he's going to give a presentation on using CUDA Shared memory. This is part 2 of a 9-part CUDA training series that NVIDIA will be presenting. So if you're interested, you might want to sign up for some of these events as well. So there are folks here in the room at Oak Ridge, as well as folks who are in person at NERSC participating up there in California, and folks listening remotely on WebEx as well. So I bring that up so that I guess if you ask questions, use the microphone so that folks listening remotely or any other location can hear the question as well as Bob, since Bob is presenting remotely. And also, if you are presenting or participating remotely, you ask questions through the WebEx chat, and Bob will stop periodically and look at that chat and answer any questions. Right, so after the presentation, we'll move into a hands-on session. For the in-person participants, we have folks on site to help. If you have questions with the example programs, we'll also keep the WebEx up for anybody who's participating remotely that wants to ask questions as well. The exercises we'll be using today you can find on the event page where you registered. There's a tab there that says exercises. Click that. You'll see a link down there where you can grab the exercises from the event. And also the slides that Bob will be presenting are also on that event page. You can find them on the presentations tab. Have it during the hands-on. Okay, and so with that, I'll hand things over to Bob and let him get started.
Indicated that is available online already. Because of that, I'd like to skip most of the preamble that I gave during that session. However, I'd like to thank my colleagues who are helping me, and I'd also like to thank Oak Ridge and NERSC for all of the support and logistics and the invitation to do this series as well. If you listened to the series last month or the episode last month, you know that I had indicated there that the first several sessions of this training sequence, in my opinion, go together. That is, I'm recommending, if at all possible, that you follow along with the first 3 or 4 sessions. After that, the remaining 5 or so sessions become more topical. However, if you miss one of the first 4 sessions, in my opinion, you're missing an important chunk of what provides the basic groundwork for CUDA programming. So hopefully you have had a chance to listen to session 1 from last month. If you did listen to session 1 from last month, you know that we introduced a basic programming example problem called vector addition. And we used that example to introduce a variety of concepts. We learned about the terminology called host and device. We learned about the global keyword. So the host and device terminology, as we know, is actually present in the CUDA syntax. It appears in the CUDA syntax. And those 2 terms are used generically to refer to activities that are taking place on the host system, in other words, on the CPU, or the device system, in other words, on the GPU. The global keyword identifies a kernel. It identifies a kernel definition. And we learned that a kernel is the way that we have as a CUDA programmer to write code that will run on the GPU and to launch that code so that it runs on the GPU. We also learned about how to pass parameters to the kernels that are running, and we learned in particular how to do memory management on the GPU. We learned how to allocate pointers in GPU memory, how to free those pointers, and how to copy data to and from those pointers from CPU memory, from host memory, using the CUDA memcopy API. We also explored launching parallel kernels, and we explored launching those using both blocks and threads individually and then combining blocks and threads together. During that session last month, I suggested that there was more to learn, of course, and one of the next topics that we want to tackle is thread cooperation and communication. And I mentioned at that point that we will need a new motivating example. So that's what we're going to introduce now. We're going to introduce our next problem that we'll focus on for for today's session. And this problem will help us to unpack and explore some new CUDA syntax and new CUDA capabilities. Before we dive into this, I'd like to mention that this will probably be quite a bit shorter session this month. And so I expect that we will have more time for questions. So if you have questions that perhaps were prompted from your review of the session last month, or perhaps from the homework that you did, today would certainly be a good time to ask those questions, and I or one of my colleagues will certainly try and answer those questions. As Tom mentioned, you can pose those in the chat at any time. I will pause maybe once or twice during this to look at the chat, and I expect that there will be quite a bit of time available in the second half of this hour for questions from the audience, if there are any. So feel free to be thinking about that while we're working through the material this month, because I'm expecting this to be a shorter sequence, a shorter session this month. So the motivating example that we're going to introduce, I mentioned that the name for it last month is called a 1D stencil. The idea behind a stencil operation is that a stencil reflects a window or a range of data, and that window or range of data is applied successively to a data set in order to produce a result. And we call that a stencil operation. And so we'll see an example of a 1D stencil as we work through this. So in order to apply a 1D stencil to a 1D array of elements, we first have to understand some characteristics of the stencil itself. The stencil is going to have a width. The width is the overall width of the window, or the width of the underlying data that will be used to make the point-wise calculation. In this case, we're imagining a stencil of width 7, and we can also define a term called the radius, and the radius is nothing more than the data that exists to the left of the stencil center point or to the right of the stencil center point. In this case, the radius is 3, and that gives us an overall width of 7. Normally, when we're working on stencil operations, we do have the concept or an idea of a center of a stencil, and so when we're talking about stencil dimensions, it's very often the case that for a 1D stencil, the width would be odd numbered. Or if we have a 2D stencil, which you could also call a windowing operation, we might have 2 dimensions that are both odd, and that would give us a very clearly defined center point and a kind of symmetry in terms of the calculations that we would perform to the left and right of the center, or to the top and the bottom of the center. In this case, we have a 1D stencil, so we're really just looking at the calculations across a 1D operation, a 1D stencil, a 1D window, and those calculations in this case will have as their focus 7 elements of the underlying data set. We imagine that the underlying data set is much longer than 7 elements. So here's an example of what could be considered a longer data set. In this case, we could imagine that these green blocks, I probably will refer to them as pixels. Just bear with me if I say that, but it's easier for me to say that than green blocks. So let's just imagine they're pixels, or they're data that is associated with a one-dimensional array. And this green data is imagined to be existing both in an input and an output array. And so we have a 1D operation. We have a set of data that we're going to transform from input to output, and the input and output sizes are the same or roughly the same. We're going to apply a stencil operation to this data set to produce the output data set, and we'll see exactly what that means in just a moment. So we could also imagine that what we're depicting on this slide, this set of green pixels or green blocks, is really just a subset of my overall data set. Remember, in CUDA, we have this idea of the hierarchical breakdown of workers, and the first level of hierarchy was the block. And so we can imagine a kernel launch consisting of a very large set of threads, and those threads are grouped into blocks. And as we'll see in a moment, we're going to be focusing on block-level behavior during this session, especially because the concepts that we're about to introduce, namely communication and synchronization, work at the block level. And so this will force us as CUDA programmers to start thinking about problems decomposed into blocks with the set of threads in the block coordinating to produce the results for that block, in other words, for that section of the data. And so in this case, we could imagine that these green pixels, these green blocks, are a set of data that is being processed by a single block. And therefore, we could imagine that the overall data set is a much longer sequence of green blocks. And this is just one subset of it, which we have assigned to a particular block. And as we saw in the first session, a very common thread strategy, especially when we're dealing with problems like this, which we could call a transform. The two canonical examples of problem types are transform and reduction for basic problems like this. Transform has the idea that the input and output data sets are roughly the same size. A reduction has the idea that the output data is much smaller than the input data set, often a single value. In this case, the output data set is approximately the same size as the input data set. Therefore, this type of problem could be called or could be considered to be in the category of problems called transformations. So we're transforming the data. The input-output sizes are approximately the same. We've subdivided our input data set into a set of elements that we're assigning to a single block. And we saw in the first episode last month that we very often have a thread strategy that assigns one output element per thread. And therefore, we might choose to break our data set down such that the number of output elements and therefore the number of input elements that are being handled by a single block is equal to the block dimension. In other words, the number of threads in the block. So we're going to choose block dim.x elements per block. And so we could imagine that the number of threads in this block is equal to the number of green blocks on this diagram. Now, what I'd like to do now is explain how the stencil operation is going to work. And so I'd like you to focus on that blue pixel or blue block in the middle. Remember, this is our input data set. And I've described the idea of a stencil operation as a window, if you will, or a stencil moving over the input data set, at each point selecting a set of values from the input data set to participate in a calculation for a single output point in the output data set. And we saw on our last diagram, our last slide, that we're imagining that our stencil has a width of 7. So we're going to start out positioning that stencil on the left-hand side of our input data set. And I've done that now depicted using the orange block. So we imagine now that that is our stencil overlaying our data set. And the stencil identifies which input elements from the top row are going to participate for the calculation of a particular element in the bottom row. In this case, the orange block in the bottom row at the center of the stencil. And so the 7 elements depicted in the top will all somehow participate, in other words, be calculated or used in a calculation to calculate the value of the output pixel, the orange block in the bottom row. Now, what I'd like you to do as I move this diagram is I'd like you to keep your eye on the blue pixel, and I'd like to ask the question, for which positions in the stencil, in other words, which input or which output points does the blue pixel contribute to the calculation for that output point? So in this case, we see that the 7 overlying or 7 orange pixels, the 7 pixels associated with our input stencil window, do not overlap the blue pixel. So for the orange pixel on the bottom, the blue pixel doesn't contribute to that calculation. But if I move the stencil window to the right, one position, to calculate our next output point like this, we see that now the orange stencil window on the input side overlaps that blue pixel. Therefore, we know that that blue pixel somehow arithmetically contributes to the calculation of the orange output pixel in the position indicated at the bottom. And if I continue to move the stencil to the right as I calculate new elements of my output data set, we see that the blue pixel is obscured for exactly 7 positions. This is no surprise because the width of our stencil is 7. And therefore, we know that for each input data item, like the blue pixel, for each input data item, we know that it contributes to the calculations for 7 different output items somehow. We haven't gone through the arithmetic yet, But nevertheless, the stencil operation and the mechanics of the stencil operation suggest that that blue pixel will somehow impact the output calculations for 7 different output points. So we're starting to see a number of characteristics about this problem which differ from the vector add problem that we looked in our last example, and hopefully you're starting to see some of the differences. In the vector add problem, a single input point only contributed to a single output point, and a single output point only depended on a single input point. And so there's quite a few differences when we look at a stencil operation. Nevertheless, the stencil operation or windowing operations in general are quite common in scientific calculations. And so this is a useful problem to consider for a variety of reasons. It's a real-world problem, and in addition, it's going to allow us to expose some additional capabilities in CUDA. So we're going to introduce shared memory now. Shared memory is going to facilitate or help us solve this problem. And shared memory is a new element in the memory hierarchy on the GPU. Now, we haven't talked much about the memory hierarchy on the GPU. In fact, all of the memory that we've been talking about from a programmer's perspective has been what we call global memory. We didn't use that word too much in the last session, but we're going to introduce it now so that we have a distinction from what we're introducing now, which is called shared memory. We now have 2 types of memory in our memory hierarchy on the GPU that we're aware of as a CUDA programmer. The first one that we're used to already, that we allocate using CUDA malloc, is called global memory. The memory that we're going to introduce now, by distinction, is called shared memory. Shared memory has a number of characteristics that make it different from global memory. First of all, global memory is typically physically implemented. In other words, the backing store for it is typically implemented in GPU DRAM memory. This is not on the GPU die itself, but consists of a number of high-speed memory devices that are attached to the GPU. Shared memory, on the other hand, is actually implemented in the GPU die itself, and so we could call it on-chip memory. Because it's on-chip, it is also quite a bit faster than global memory. And so when we access shared memory, both the bandwidth and the latency that we can expect are higher and lower, respectively, higher bandwidth, lower latency, than what we would typically experience when we're going to global memory. Those concepts of bandwidth and latency are something that we haven't spent too much time talking about yet. We'll cover those in the next 2 sessions. We will take a much closer look at memory performance in the next 2 sessions. But for now, it's sufficient to say that shared memory, from a performance perspective, typically has a behavior that allows it to be much faster than global memory. It's very fast, like on the order of 5x faster as a rough rule of thumb or guide. It's also got a characteristic meaning that it is user-managed. We'll see what that means in a minute. We could use user-managed here to distinguish or differentiate from the idea of a cache, which is also an on-chip memory, which is also very fast, but is not explicitly user-managed. Instead, the hardware decides what goes into the cache. You could imagine that shared memory, and sometimes shared memory is described as a fast user-managed cache. Shared memory also has some important logical distinctions. Shared memory is declared using the shared keyword, _shared_. And it is a per block resource. Now we know what a block is already. That's our first level of subdivision of the CUDA grid, the set of all threads associated with a kernel launch. And shared memory, when we define it, is a per block logical resource. What does that mean? It means that for a given block of threads, they have a view of shared memory. In other words, they have their own local copy of shared memory, if you will. And when they read and write data from shared memory, they only read and write data that is written by other threads in that block. When we move to the threads in a different block, they have their own local copy of shared memory, and there's no connection between the two. So if threads in block 0, let's say, populate shared memory with all zeros, and then threads in block 1 populate shared memory with all ones, when threads in block 0 go to read shared memory, they'll read all zeros. Their view of shared memory is completely unperturbed and separate from the view of shared memory in block 1 or any other block. So it's a local per block resource. It is a logical per block resource. It's declared using the shared keyword, and it is also allocated per block. Each block, therefore, has somehow an allocation of shared memory, which is unique and specific to it. So what we're going to do is we're going to take advantage of shared memory to do some caching. In other words, to make data available more readily for reuse. This is a pretty straightforward concept. It's not unique to GPUs or CUDA programming at all. In fact, any computer architecture that has a memory hierarchy, in other words, memory at different levels that may have slower or faster performance and may also have other differing characteristics. It's a common computer science optimization across a wide range of computer architectures that says that if we have data reuse, we may be able to accelerate that algorithm by moving the data that's to be reused to a higher level in the memory hierarchy. In other words, closer to the processor to a faster memory resource. That's exactly the way that we describe shared memory, and that's exactly what we're going to do here. Why are we doing it here? We saw that in the previous diagram when I was moving the stencil over the data set, we saw that the blue pixel was used to calculate the results of 7 different output pixels. That's exactly a definition of data reuse. So each data item in our input data set is used in 7 different calculations to calculate 7 different output pixels. That is data reuse. Now, rather than loading that data 7 times by 7 different threads or for 7 different calculations from global memory, which I've indicated now is a slower resource than shared memory, instead what we can do is first load the data into shared memory, and then when we run our 7 different calculations, we access it from shared memory instead of global memory. And in so doing, as a result of the data reuse, we pick up speed benefits. We pick up performance benefits. Now, there's some other reasons to do it as well, which we will see in a moment. Some logical reasons, some programmatic reasons why it's appropriate and sensible for us to use shared memory to arrange for this sort of calculation. But our first concept is that we want to cache data in shared memory. And so what we will need to do from a programming standpoint is we will need to read a block's width of data from our input data set, which is in global memory, and store it in shared memory. Now, in addition to the block width of data, because of the nature of our stencil operation, we're going to need what's called a halo, or some additional radius pixels or input data elements on the left and the right-hand side of our data set. Now, the data set that I'm talking about here and the data set that I depicted at the bottom of the slide, as I mentioned on the last slide, is something that we might consider to be the subset of data that's being managed by a particular block of threads. It's not necessarily our entire data set. That's what I'm talking about when I'm looking at the green pixels on the bottom. Therefore, the input data set is presumed to be larger than just the green pixels on the bottom. We can imagine a very long line of green pixels on the bottom, which represents our 1D input data set. And therefore, when I talk about pulling the halo on the left and the halo on the right, the orange pixels that I've depicted on the bottom diagram as additional elements that we need to load, those are really just coming from the rest of our data set. They're just neighboring elements in our data set, which is imagined to be a very long line of green blocks or pixels. So when I say I'm loading the halo on the left, that's just moving to the left, if you will, in the data set, or moving to the right in the data set, and providing some extra storage in local memory, in other words, in shared memory. And the reason that we do that is if we focus on the bottom green line of pixels, this is our output data row now, and we look at the pixel on the very leftmost position, in order to compute that pixel position, we need at least 3 elements to the left on the input and 3 elements to the right on the input. In order to satisfy those 3 elements on the left, we are loading this halo, these extra elements around our core data that our block is processing. This is a very common operation. The idea of a halo, the idea of loading additional data around a core data set, is a very common operation in scientific computing. So there's a good chance that you've run into this idea already in your programming journey. So we're using it here, and we will use it here, we need to load some additional data on the left and the right to make our stencil calculations work so that we can calculate one output element per green input element that we have assigned to this thread block. Therefore, we're going to compute blockdim.x elements, in other words, one output element per thread, and then we're going to write, once we've computed those, we're going to write those values back out to global memory. This is starting to talk about our strategy for code development now to solve this problem. As we've indicated already, each block needs a halo, and that halo is of size radius being the number of elements to the left and right of the center position in our stencil. Okay, so let's take a look at what this code would look like to achieve those objectives on the previous slide. First of all, we need to declare shared memory. So this is not something that's available automatically. It's something that we have to declare. There's a couple different ways to declare it. What we're showing here is called a static allocation of shared memory. It's discoverable and identifiable and definable at compile time. It is also possible to do a dynamic allocation of shared memory, which in some ways looks similar, but allows you the flexibility to have a variable-sized shared memory array, the size of which is determined at runtime. Okay? But for the moment, since we're just introducing shared memory, and for many situations where you might want to use shared memory, it's sufficient and it's very conceptually easy to understand if we use a static allocation here. So the static allocation of shared memory effectively creates a new logical memory array whose name is temp, and it's of type int. And the size of that array is what's depicted in the square brackets. So it's the block size, the number of threads in my block, plus twice the radius. And we saw the reason why we are choosing that particular size for shared memory. We saw the reason for that on the previous slide. And so we're choosing a shared memory size which is equal to the block size plus a little bit bigger to store our halo or radius elements. That shared memory doesn't have anything in it yet. That's just a declaration that we can use. We will need a global index. Now, previously, when we talked about creating a globally unique thread index, I didn't really stress the word global too much. But now that I'm using the word global and calling this G-index, that's just a name, the idea is that this will be an index which will be primarily used for retrieving or storing data in global memory. In other words, it has the ability to index across the entire input data set. And therefore, we're going to construct that index in exactly the same way we constructed it when we got towards the end of the session last time. This is our canonical method for calculating or creating a globally unique thread index in the 1D case. Threadindex.x plus blockindex.x times blockdim.x. We're going to assign that to a variable G-index. Now, that is useful for retrieving data from global memory, but it's not as useful for retrieving data from shared memory. First of all, shared memory is not the same as global memory. It's in a different place. But more importantly, shared memory is of a different size. It's a much smaller size. The amount of shared memory that we're reserving per block is just the amount of shared memory we need to store one block's worth set of elements from our input data set, plus the halo. And so the shared memory is fundamentally of a different size. It does not numerically extend across the entire range from an indexing standpoint that our input data set spans. And so we're going to use a different index for that. And this index, perhaps evidently, will be based on our threadindex.x. Remember, the threadindex.x variable is a variable that is unique within a thread block. In other words, each thread within the thread block has a unique value for threadindex.x, and that value goes from 0 to n-1, where n is the number of threads per block. And so this gives us a very convenient indexing base, if you will, to index into shared memory, our temp array, because our temp array is equal to the size of the block, plus a little bit, okay, plus the halo or radius. And so we're going to basically say that each thread will start out with an L index value that's equal to its thread index plus the radius. This will offset it into the shared memory array. And we'll see how that makes sense as we use that index. So the first thing that we'd like to do, as we said on the previous slide, is we'd like to load our data from global memory into shared memory so that we can cache it. In other words, so that we can take advantage of shared memory from the standpoint of having the data available locally for performance reasons. And so we're going to do that actually with a single line of code. We're going to say temp of L index equals in of G index. And that one line of code will be responsible. It will accomplish the loading of all of the green pixels that I've depicted on the right. So whereas shared memory started out with quote unquote not anything in it, empty if you will, in other words uninitialized, this line will initialize in a single line of code all of the green pixels or all of the green blocks that I've depicted on the right-hand side. In other words, everything except the halo. And there's no for loop. It's a single line of code. How does this work? Well, we have to remember that when we write code in CUDA, typically it's not just a single thread executing that code. At the moment, our focus of attention is within a thread block. And so we remember that this particular line of code, even though there's no for loop, is executed by each thread in our thread block. Therefore, it populates all the green pixels in that one line of code. Next, we have to populate the halo. And so we're going to select a number of threads. In this case, select a group of threads such that the size of the group is equal to radius, in other words, 3 in this case. And we will write some additional code which will populate the left-hand side and right-hand side halo regions of our shared memory. We've now finished loading our input data into shared memory so that we can use it for our calculations. Okay, let's continue. We're now ready to complete our calculations, and now we need to apply the stencil. In other words, we need to perform a calculation across the stencil width of the input data set, which is now located in shared memory, in other words, in the temp array. And in this case, we are using a for loop. Why are we using a for loop here? Well, in the previous example, on the previous slide, we only needed to load one input element per thread, and we needed no loop to accomplish that. In this case, each thread is responsible for reading 7 elements, in other words, the stencil width, out of shared memory from our input data set, which has been cached in shared memory, and then calculate a result based on that. And in this case, the result is simply the sum of those 7 elements. Okay? So we do need a for loop. Each thread is executing this for loop now. Each thread is iterating over 7 elements of the temp array, adding them together to store them in a thread local variable called result. And when we're done with that operation, we store the result value back out to global memory using our global index. And if you work through this indexing, you'll see that the L index plus offset, where offset is spanning from minus radius to plus radius, gives us exactly the operation we desire, so that each thread is accessing a set of 7 elements. Each set is offset by 1 as we move through the thread array, through the threads in the block. Unfortunately, this doesn't work. And the reason it doesn't work is probably perhaps not immediately obvious or evident to you yet. When we looked at this diagram, and we said that the first line of kernel code that does anything, loading from in to temp, in other words, populating our shared memory, we just depicted all of those green pixels, all of those green blocks, all at once. And in some sense, you can think of it happening that way. However, we need to introduce an important new concept in CUDA programming, which wasn't really that evident in our previous example with vector add. That new concept is that threads in the CUDA programming model do not all execute together. The simplest way I can describe it is that there is no prescribed or guaranteed order of thread execution. Therefore, from a programmer's perspective, you should assume that threads can execute in any order. Now, as you get farther into CUDA programming, you'll discover that that isn't really true, but the way that it's not really true has to do with the implementation of CUDA, not the CUDA programming model. Therefore, to be a good programmer, The important thing to lodge in your understanding of CUDA is that threads can execute in any order. If I, as a programmer, do not provide any mechanism to manage the order of execution of threads, they should be assumed to execute in any order, and my program must produce the correct output regardless of thread execution order, or I have a defect in my program. So when we apply that concept to what's going on here, what we can observe is that, let's go back and look at our code now. We're loading shared memory, and we had sort of previously, we may have had this mental model that said all threads are sort of executing these lines of code in lockstep. In other words, every thread executes a line of code, then every thread goes on to the next line of code. That's not the way it works, and that is not the CUDA programming model. The way it works is threads can execute in any order, so let's try and come up with a worst-case scenario. Thread 15 gets to this line of code and runs, in fact, through all of this code before any thread gets to the line of code that we're depicting here. So somehow, thread 15 raced ahead of the other threads. Okay, this is just a mental example that we're making up here, but it's a perfectly good example for finding the defect in this code or for understanding the defect in this code. So thread 15 is the only thread marching forward at this point. So thread 15 does its job for each of these lines of code, and in the first line of code, it loads the green pixel that we depict on the right. And in the subsequent lines of code that have to do with loading the halo, thread 15 isn't selected, so it doesn't do anything. It doesn't participate in those lines of code. And then thread 15 runs on and begins to perform its for loop. Okay, there's nothing to prevent thread 15, according to what we've written. There's nothing to prevent thread 15 after it's done its job for loading shared memory to go on and begin processing the for loop. Now, I haven't depicted the entire for loop on this slide, but one of the operations in that for loop will be to take our result variable, initialize it to 0, and then start adding to it elements from shared memory. Now, those elements from shared memory include the value that thread 15 loaded, but they also include values to the right and to the left. And since those other threads that were responsible for loading the values to the right and to the left have not reached this point yet, those values are uninitialized. Thread
Bob, it appears we've lost your
address it is what's called a barrier. In this case, we're talking about something called an execution barrier. So sync threads is the execution barrier that we're going to introduce. And sync threads is an execution barrier for all threads within a block, not the entire grid. Sync threads does not force all threads in all blocks to reach a point. What sync threads does do is force all threads in a block to reach the sync thread statement before any thread is allowed to proceed beyond that statement. This is a classical execution barrier, but it runs at the block level. It does not operate across blocks. That's important to keep in mind when you're thinking about synchronization. So sync threads, as it turns out, is just what we need to prevent this kind of a hazard. This hazard could go, sometimes might be described using naming conventions like RAW, read after write, or write after read, or write after write, different kinds of hazards that arise in a multi-threading environment when threads can race ahead of each other, when threads are not in sync, so to speak. So sync threads can help us fix this problem. All threads have to reach the barrier before any thread is allowed to proceed beyond the barrier. Now, we've seen an example of conditional coding already where we are choosing, in this case, a set of threads based on the thread index. So in this case, within the if statement in our code right here that I'm depicting on this slide, only a certain number of threads are participating in the loading of the halo region. It's 3 threads, actually, in this example. Not all the threads in the block. This also points out an important requirement for the use of sync threads. Whenever we use sync threads in conditional code, the condition must be uniform across the block. What that means in a nutshell is that all threads must be able to participate and hit that sync thread statement. Now, we're not actually going to use sync threads in this way. In other words, we're not going to use it within a conditional region within this particular problem or example, but I want to point that out because it's a common mistake that people make, and it means that you have created a bug in your code if you do so. In many cases, it will not be that evident that you have a bug in your code, but it is nevertheless illegal coding, and eventually it may bite you. However, that's an aside because the way that we're going to use sync threads to fix our problem at hand does not require the use of sync threads inside the kind of conditional code that I just depicted. But we can use sync threads in a very straightforward fashion, and hopefully you can figure out where it ought to belong to fix our problem. We stated that all threads need to load shared memory, and then threads go on and process their individual for loops to calculate their elements. So the conclusion is that we want to make sure that all threads have loaded shared memory to make it coherent with the input data set and global memory. We want to make sure that all threads have loaded shared memory so that no thread will pick up uninitialized or invalid values. Once all threads have loaded shared memory, then we can go forward with our processing of the for loops in whatever order. Doesn't really matter at that point. And so the logical place to put a sync threads to fix this will be right here. In other words, right after we have loaded shared memory, but before we go on to do any processing of data from shared memory. And in fact, this will be a canonical pattern that you will see a lot in CUDA codes that use shared memory. We will collectively load shared memory. Then we will put a sync thread statement that's not in any sort of conditional block. And then we will go on and do the processing that we intended to do using the data in shared memory. That's a very common pattern. And if you don't see that pattern, if you see that missing somehow, that should sort of raise a question mark in your head, like take a close look at that. It's not to say that there can't be any cases that don't require an intervening sync threads between the loading of shared memory and the use of data from shared memory, but it's just not that common, and so you should be on the lookout if you see a missing sync threads in between the loading of shared memory and the use of data in the shared memory. And if you're loading and using shared memory in a loop, it can get even more complicated. You may need to bracket certain operations with sync threads so that after threads have done their calculation and they're about to go on and reload shared memory, you have a sync thread that prevents those threads from racing ahead until everyone has had a chance to use the previous iteration or previous load of shared memory. But in this simple example, we're just doing one shot of operation. We're going to load shared memory, we're going to call sync threads, and then we're going to perform the same processing that we depicted before. And if we do that, everything just works. So to review then, shared memory is a local on-chip resource. It's a per block resource. We allocate it using the shared keyword, _shared_. And it has actually size limits that we haven't talked about. So shared memory is limited to something on the order of 48 kbytes per thread block. So that's something to be aware of. Global memory very often has sizes associated with it that are in the gigabytes range. We can't load a gigabyte of data into shared memory. Okay, so shared memory is, in that sense, something like a cache. The programmer will look for opportunities to use a smaller subset of the data that can be loaded into shared memory and used in an efficient fashion, probably in a scenario where there is data reuse, used in an efficient fashion in order to accelerate your code. In many cases, as we've seen in this example, when we need to use shared memory, we will also need to use sync threads, especially if we're doing a collective load of shared memory and we have threads that are communicating with each other. So we've introduced now the two concepts. One concept we've introduced in clarity, that is sync threads. That's synchronization, inter-thread synchronization. And for the most part, inter-thread synchronization in CUDA is only provided at the block level. We've talked about that already. So that's our first concept that applies to blocks, but not the entire grid. So we're starting to see a distinction in the capability of threads when we're talking about threads within a block versus threads that are in different blocks. Threads within a block have the ability to synchronize with each other. Now, the other key characteristic of threads within a block that is not the same of threads between a block is the ability to communicate using shared memory. Whenever one thread loads data into shared memory and another thread uses that data, we call that communication. Now, communication can happen in global memory as well. Global memory is visible to all threads, and so it's possible for threads to communicate in global memory, but it's much more common for a variety of reasons for programmers to use shared memory when they need to pass data from one thread to another. Okay. I'd like to mention a few things because CUDA has developed over a period of in excess of 10 years now. And as it's developed, new mechanisms have come into play. New mechanisms have been developed that are useful from a programming perspective, but that may cause your view of certain characteristics to change. Now, we've spent a fair amount of time talking about shared memory, and we talked about one of the characteristics of shared memory. I'm sorry, we talked about one of the characteristics of thread blocks, that thread blocks have the ability to synchronize with each other. So synchronization is an important characteristic. You may think that sync threads is the only way to synchronize threads, and it used to be that was the case until recently, until about CUDA 9, I believe. In CUDA 9, we introduced something called cooperative groups, which gives more flexible synchronization primitives that are available to the user. We're not actually going to cover cooperative groups until the last session in this series. So I think right now we're scheduling that session for September. But I want to give you some advance notice that sync threads may seem a little bit restrictive right now, and some of that restriction is going to be eased up when we get to cooperative groups. So your ability to flexibly synchronize threads within a block as well as threads across blocks is going to be improved when we expose cooperative groups. The other thing, so cooperative groups will introduce a number of capabilities. I don't think we need to go through them all right now, but cooperative groups will provide a number of characteristics associated with groups of threads that are working together that allow us to write flexible algorithms. And so we'll dive into this in much more detail when we get to the last session in this series. The other thing I want to mention about shared memory is the idea that I introduced right up front, and that is that shared memory is very commonly used as part of the memory hierarchy to speed up algorithms where there is data reuse, and that concept is not unique to CUDA. It's a very common programming optimization concept in a wide range of computer architectures. However, I want to point out that processor architecture, in particular GPU architecture, has proceeded quite a bit from the early days of CUDA GPUs. We've had 10 plus years to improve our GPU processing capability, and that's come in a variety of forms. One of those forms is by increasing both the performance and the size of our caches, our on-chip GPU caches. And I mentioned that shared memory in some ways could be described as a user-managed cache. The cache idea comes about from the idea that I can only map a limited subset of my large input data into shared memory. And so as a programmer, I have to be selective about the data I bring into shared memory in order to provide the most benefit. Caches attempt to do the same thing, but they don't do it explicitly. They do it based on the pattern of activity of your program and attempting to hold recently accessed data in the hopes that it will be reused in the near future. That's the idea behind a cache. Early GPUs had essentially no caches. The very first CUDA GPUs basically had no caches, and yet they delivered performance that was interesting to people. Since then, of course, we've added caches to the GPUs and we've increased the size of caches. And so when we talk about processors like GB100, Volta, the processor that's in Summit and Sierra, for example, those processors have a sizable L1 and L2 cache. And what that means is, from a performance perspective, the performance benefit that you might have associated with a typical shared memory optimization may be reduced in a processor like Volta because the L1 is larger and more performant and more flexible, and so it can effectively do the job that shared memory was doing for you in terms of performance. Now, that doesn't speak at all to the synchronization topic that we talked about. I'm just exposing that from a performance standpoint. Okay, so we've reached the end of the session. I'm going to take a look at the chat first. And I think we have talked about, okay, let's see. How is shared memory organized in comparison to global memory in hardware? Well, that's a fairly involved topic. First of all, I mentioned already that global memory is the physical resource, the backing store, if you will, for global memory is DRAM chips that are adjacent to the GPU but not part of the GPU die. They're physically connected to the GPU, but they're not part of the GPU die. And so global memory, first of all, typically is larger than shared memory in terms of how much you can store there. And also, it's typically slower. And also, it has characteristics associated with it that are DRAM-style characteristics. I'll try and give a couple examples of that. First of all, when we're accessing DRAM memory, this is not really that relevant to the CUDA programmer. It's not immediately obvious to the CUDA programmer, but it is important from a performance standpoint. And so I want to point out that as I discuss these things, I'm going to hopefully provide considerably more clarity on the distinction between DRAM and what affects the performance of data in DRAM versus shared memory and what affects the performance of data in shared memory when we get to our next two sessions. Okay, our next two sessions are going to take a deep dive or a deeper dive on GPU architecture, and in particular, we're going to be looking at memory, both shared and global memory. And we're going to talk about the performance characteristics, the hardware performance characteristics of those memory types and what the implications are for a CUDA programmer. So we're going to do a better treatment of this topic in the next two sessions, but I'll briefly summarize some key points. Global memory is typically backed by DRAM. DRAM has DRAM characteristics. When I'm dealing with DRAM, I don't get to ask for a single byte or a single word or a single int or a single float or a single double. That's not the way DRAM works. DRAM says, which group of 32 bytes do you want? You tell it which group you want, and then the DRAM sends 32 bytes back at you. If you needed 32 bytes, great. If you only needed 1 byte, you still get 32, and you've still used up 32 bytes of transfer on the DRAM bus. So DRAM has characteristics that are largely emanating from that single idea. You get to access DRAM by segments, not by bytes. Okay, and we'll talk in more detail about what segments are and why that's important when we get to our next two sessions. When we're talking about shared memory, it's implemented on chip. It's not fundamentally a DRAM structure. It's a different kind of structure. If you're an electrical engineer, you could sort of imagine it's something like static RAM. And it has some architectural design characteristics of its own. In fact, it's fundamentally, the way I like to describe it, underneath the hood, is that it's fundamentally a two-dimensional array of memory. And we'll see why that viewpoint, why that statement makes sense when we take a closer look at DRAM memory operations. I'm sorry, when we take a closer look at shared memory operations in the next couple sessions. But this two-dimensional array of static RAM on the device, which serves as the physical backing store of shared memory, also has some access characteristics. You can ask for a single set of 4 bytes if you want. And in fact, you have a flexible way of asking for groups of 4 bytes from a variety of different locations in DRAM, in SRAM memory or in shared memory. When we're talking about global memory or DRAM memory, we don't get to choose different locations. All 32 bytes have to be contiguous. Okay, but with shared memory, that requirement for contiguous access is broken, and that gives us some additional flexibility, but it also gives us some additional things that we need to focus on if we're interested in maximum performance from shared memory. So we'll dive deeper into those details in the next two sessions, and I ask you to hold the remainder of that question when we get to the next two sessions. Does every thread reserve the same amount of shared memory? So a shared declaration is not really a per thread declaration. It's a per block declaration. So when I say double underscore shared double underscore, that's really a signal to the compiler or to the machine, if you will, that says reserve the amount of shared memory that I've indicated here for all the threads in the block collectively. It is not a per thread allocation. It's a per block allocation. And an individual thread does not reserve shared memory. That concept of a thread reserving something would be something like a dynamic allocation. And what I've started out to say is the way we've described it here and used it here for the moment is a static allocation, okay? So it's really something that's carved out and made available to the machine or to the thread block without the threads having to do anything at all. Also, does loading from global to shared memory also load neighboring locations? Well, I mentioned previously that accessing global memory is basically accessing DRAM. And in DRAM, you don't get to ask for a particular location or a particular byte or a particular int or 4 bytes. You get to ask for 32 bytes at a time that are called segments. And if you only need 4 bytes, you're still going to get 32. So in that concept or in that context, you could imagine that loading data from shared memory, from global memory, will involve the retrieval of adjacent locations. Now, when we get into our next 2 sessions, we're going to understand better what that means, and we're going to understand better how to take advantage of that and make that be a performance boost instead of a performance limiter. Take best advantage of the use of our memory subsystems on the GPU. That's a key focus for the next 2 sessions. Okay, so yes, loading from global may involve loading neighboring locations. It does not involve storing those locations unless your code explicitly stores those locations. How does the CUDA runtime handle memory locations that are being read by multiple threads? In a nutshell, there's a broadcast operation. So if I have 2 threads reading from the same location, whether that's in global or shared memory, there's broadcasting. That means that both threads will receive the same value, and there is no performance detriment to so doing. Now, we're going to talk about broadcasting in the next session when we talk about the hardware interaction of memory with the CUDA programming model. So if you'd like a deeper treatment of that, I encourage you to attend the next 2 sessions. But from a reading standpoint, 2 threads reading from the same location indicates no particular hazard. No particular hazard in terms of the validity of the results, no particular hazard in terms of the performance. Is there any known performance difference between using dynamically allocated shared memory and statically allocated shared memory? Not to my knowledge. They work identically. The question is regarding the previous session. Can you explain once more the conceptual distinction between grid, block, and thread and how they are connected? Okay. The grid is the set of all threads associated with a kernel launch. And when we have a kernel launch, let's see, do I have a kernel launch in this slide set? If not, I can switch to another slide set. Let me pull up another slide set from our previous session. Actually, that's not it. Well, this will do. Just a minute. So this isn't exactly the slide from our previous session, but it's close. This shows a kernel launch, the add kernel. The kernel is named add. And we remember that the triple chevron syntax specifies launch configuration. Basically, the number of threads. For this purpose, for this level of instruction, it specifies the amount of threads are associated with the kernel launch. Now, it does that by specifying 2 numbers. The first number, in this case, the orange number n, represents the number of blocks that are associated with a kernel launch. And the second number, 1, represents the number of threads per block. Those numbers are both adjustable variable and can be runtime variables. So when I launch a kernel, conceptually, we're launching a set of logical workers that we refer to as the grid. The grid is the collective term that identifies all the logical workers associated with a kernel launch. The number of those workers is specified by the 2 parameters that we have in this kernel launch syntax, the first one being the number of blocks and the second one being number of threads per block. So if I imagine a kernel is spinning up a grid, the grid is a single entity. That entity can be subdivided firstly into a set of blocks. So a single grid might consist of 8 blocks, or 64 blocks, or 100 million blocks. The second level of subdivision is I can break each one of those blocks into a set of threads, and the maximum number of threads that I can have per block is 1024. The minimum is 1. So in my simplistic example, if I launch 8 blocks of one thread, then I have 8 total workers. I have 8 total threads. If I launch 8 blocks of 8 threads, then I have 64 workers, 64 total threads. So hopefully that is enough of a refresher from the previous session. It seems to me like we've gotten to the end of our chat session. So are there any questions that I can answer live?
Hi, Bob. This is William Pan. I noticed that you mentioned about static and dynamic shared memory earlier. So how do we do dynamic shared memory? Is it there is like some kind of equivalent to like CUDA malloc, but for shared memory?
Okay, it's a good question. I think the easiest way for me will be to just show you an example. So I'm just going to type, if that's okay.
Yes, please go ahead.
If I have an ordinary kernel, I might say global void k with some parameters. And if I was going to declare shared memory statically, like we have, I would say double underscore shared, double underscore, the type, so we could say it's int or float or whatever, the name of the shared memory, and then the size of the shared memory. Okay? And in this case, the size is interpreted just the way you'd expect for array. In other words, it's the number of array elements of size int. So if my size is 48, that would be a total of 192 bytes of shared memory that's allocated using this statement, which would be a static shared memory allocation. And if I'm launching kernel K like this, I could launch it in my host code quite simply, like K, 1, 2, 3, grid, block, like that. That would be an appropriate kernel launch for kernel K with a variable called grid, which is defining the number of blocks in my grid, and a variable called block, which is defining the number of threads in my block. Now, when I switch to dynamic allocation, my kernel looks a little different, or the shared memory declaration, I should say, looks different. Instead of this, what I'm going to do is quite simply that. Okay? That has now become a dynamic shared memory. That's an indicator to the compiler that this is now, this statement right here is now reflecting a dynamic shared memory allocation. By itself, it's allocating 0 bytes. Okay? So there's some other work that's needed. And the other piece of the puzzle here is when I launch this kernel, I have to provide an additional parameter at kernel launch time, which goes in the triple chevron syntax. It's the third parameter, and it defaults to 0. Okay? But the third parameter in the triple chevron syntax is shared size in bytes. Okay? Now, this is just like grid and block can be, shared size in bytes can be, it doesn't have to be a compile time variable, it can be a runtime variable. So I could have a variable called int shared size in bytes equals some calculation. Okay? And since I don't want to dream up a calculation, let's just say I said this was 192 for now. Obviously, that's known at compile time, but it doesn't have to be. Okay? These two formulations are now equivalent if I had a statement like this. So here we have static and from here on we have dynamic. Does that help?
Yes, thank you.
Okay. These two formulations that I've realized from the standpoint of the programmer's code, in other words, what's going on in the triple dots here, should be identical. There's no reason that that code should have to be any different, whether I have this sort of declaration or this sort of declaration. No reason that the triple dot code has to be any different, and no reason that I would expect the performance to be any different either. Now, a common mistake when people switch to using dynamic shared memory is they do this and they forget to do this. And they wonder what's going wrong. Why is my code not working? Okay, so that's something to be aware of. Anytime you use dynamic shared memory, if you don't have a third parameter in your kernel launch, it's guaranteed that your code is broken, unless you're not actually using shared memory at all. Okay? Because this defaults to 0 and you'll get an array. The symbol is there. The pointer is there. The array is there, but it's of size 0. That won't be useful. Okay? Okay, any other questions?
I have a question. Inside the kernel, is there a way to find out what is the size of the shared memory? I think there are specialized registers in PTX.
Yes, there are in PTX, but I'm not aware of any to do it in CUDA. So I'd rather not try and drill into that because we would basically have to have a discussion of PTX, which isn't really the focus of this. So if you need to know the size of shared memory in your CUDA code, in your kernel code, my recommendation would be to pass it as a parameter. Okay? And then you can use it here. Okay, does that make sense? Hope that makes sense. Are there any other questions?
I don't see any other questions here at Oak Ridge. Are there any questions in California? Any questions remotely? Whether you want to ask through your microphone or in the chat?
No, I think we're good, Tom.
Okay. Well, I think we can wrap it up for today. If you are able to do the homework, I would encourage it. There's just 2 problems in this homework session, and some of the benefits, if you will, of doing the homework are that you could explore the benefit of shared memory. In other words, I mentioned right up front that shared memory, one of the benefits of shared memory, of course, the structural benefit is it allows you to do things like synchronization and inter-thread communication. If you need to do those things, there's really no replacement. But another benefit of shared memory, as I mentioned right up front, is that it may have a performance benefit. If you use it as a user-managed cache in an intelligent way in a data reuse scenario, then presumably it should make your code run faster. If you'd like to explore that, the homework gives you an opportunity to do so. The second example in the homework is a matrix multiply example that extends a similar problem in the first homework session. So in the first homework session, you were challenged to write a naive matrix multiply, and the principal thing that we were exposing there was how to handle 2-dimensional grids. In other words, how to handle a 2-dimensional problem using a 2-dimensional array of threads and the mechanics associated with that. That was the principal idea in homework session 1 in the matrix multiply example. If you choose to do homework session 2, today's homework, you'll have an opportunity to recast that using shared memory. Most of the work is done for you, but you will complete that exercise and verify that you get the correct results. In addition, if you wish to, as an additional exercise, it's not spelled out in the homework, but if you did the homework exercise from problem 1, or even if you didn't, you can just go back to problem set 1 and look at the solution that's provided there, and copy the kernel, which is complete in the solution, copy the kernel and drop it into homework set 2, and use that kernel definition in place of the one that uses shared memory. Then you can see what the performance difference could be. And I think what you'll find is that it's not zero, so shared memory does provide some benefit, but how much benefit, you can be the judge of whether or not it's an interesting optimization. There's a lot more to that particular idea. To really understand the performance and do performance analysis and understand what's going on and figure out how much benefit we get from shared memory from a performance perspective, for example, in that matrix multiply problem, we would want to do a more careful analysis than just the crude timing analysis that's provided for in the code. But nevertheless, you could get started with that, and I believe that you will find that shared memory does make that run faster. So that's an opportunity for something that you can play with and explore in today's homework assignment if you choose to do it. So with that, I think we're at the end of our session. I appreciate your attention. I hope you found it useful. I really do hope that you will attend the next 2 sessions because, as I mentioned, they will sort of round out a basic treatment of what I consider to be the fundamentals of CUDA programming. And so hopefully I look forward to seeing you during the next 2 sessions in March and April. So with that, I'm going to sign off, and once again, thanks to Oak Ridge and NERSC for making this possible.